Good morning, everybody, and thanks to the organizer for organizing this wonderful meeting. So I will be talking on a completely classical system, or we will see some of the analysis and the results that we get are very similar to what we have typically seen in quantum chaotic systems, and I think these results are interesting to share with you. So what I will be doing, I will be studying the Lyapunov spectra of coupled oscillators. So we'll be dealing with chaotic systems, and by chaotic systems we mean that if we put in a small perturbation, the perturbations grow exponentially in time, and they are typically characterized by some numbers called Lyapunov exponents. Now, so how do we calculate them? So if we find the rate of change of these perturbations for some oscillators, then it is typically done in terms of the Jacobians. So we now take a product sum of all the successive Jacobians evaluated in the successive time steps. Then we construct a matrix, a P of t, which is known as the oscillator matrix. And if we diagonalize these numbers, then logarithm of these eigenvalues gives us the Lyapunov exponents. Now see, for n-dimensional systems, we don't have one exponent. We have n such exponents. Typically, one is happy if they see at least one, and they say the system is chaotic. And they also say that if the sum of the positive Lyapunov exponents they associate with some number, they get some number which they call the Kolmogorov-Sinai entropy. And the rest of the spectrum typically is much ignored in dynamical systems analysis. So what we are going to do, we are going to monitor this Lyapunov spectra for n-dimensional coupled oscillators in presence of some disorder. Disorder means some randomness in some parameters. Okay. So to start with, let's do a very simple system. So let's forget this coupling part for time being, say epsilon equal to 0. So what we have are two coupled systems, two-dimensional coupled systems, and I can go from 1 to many, say 6 in this plot, and they are standard maps. Standard maps are typical prototype systems which are studied for studying chaos in Hamiltonian systems. They are essentially kicked oscillators moved, which are monitored stroboscopically. And the parameters here, k, depending on their magnitude, if they are typically in this region, say 7 to 10, the system is going to be chaotic. That is, and below that, it will be non-chaotic, that there will be periodic orbits. And if you change my parameter k and bring it to this regime, all the periodic orbits will be broken, and the space will be completely irregular. So what is done here? So suppose I have 6 such systems. I vary, and for each of these systems, I assign some ki0 taken from this range. I assign some ki1, and I vary them continuously by varying a parameter tau, which goes from 0 to 1, and I compute the corresponding Lyapunov exponent. So they go to some positive number, and in this range, they show some linear dependence. So this is a typical Lyapunov exponent curve as a function of tau as I go from ki0 to ki1. Now, since I have so many other systems as well, for all of them, I get 6 such curves, and since they don't interact or they don't talk to each other, they cross happily at many locations. Okay, now I tune on this coupling, and the coupling, even though it can be very small, then what is seen that the evolution in one direction begins to feel the presence of the other one, and then there is something quote-unquote repulsion. So this type of systems for n equal to 2 and can be very analytically studied. It was done quite some time back, couple of decades ago by Dido. And this for 6, at least till up to 5 and 6, it was done by Pikovsky. And what they call this thing is coupling sensitivity with chaos. So this is apart from the sensitivity of the system to the initial conditions, that's my system is unstable, Lyapunov unstable, but they also show some sensitivity to the coupling. Now what we are interested in now, suppose we calculate these gaps between these levels, between two successive Lyapunov exponents, so we can calculate the gap, say SI, and let's see what the distribution looks like. Does it show something that we see in the quantum chaotic systems? We'll come to that thing in a moment. So what our system that we are going to study is will be randomly coupled Kuramoto oscillators. Kuramoto oscillators are nice in the sense that they are much well understood in terms of seeing transition to the synchronized state. So if you take the traditional Kuramoto oscillators where all these numbers are equal to 1, this coupling matrix, all the elements here are equal to 1, then I have the, let's call it say traditional Kuramoto oscillators. And in absence of the coupling, these are the phases of some oscillator which are given some random number, say omega n. It can be taken from any distribution. Here I just show it for taken from say uniform distribution. So all of them now oscillate independently with some frequency omega. Moment I put on this coupling, then they go from a completely disordered or incoherent state to a ordered state or a synchronized state. It is also possible for this case, at least we can calculate the Lyapunov spectrum explicitly, and it turns out this function. This is not important for this talk, but what I would like to say that there will be one regime where if the oscillators are all going randomly with respect to each other, the corresponding Lyapunov exponent will be 0, or there will be a negative part. The function will depend on what type of functions I choose over here, but they indicate the synchronized state. Now we'll study this type of model, which will be random oscillators, randomly coupled oscillators, and we'll choose this matrix with a certain property. Certain property like, we'll choose this matrix because you see there are two things that we can vary now. One is the strength of this coupling, and we can vary how the range of this coupling by taking some banded matrix, okay? So we'll take some random banded matrix, and they can be, they are symmetric, and they are, in the random matrix theory, they are typically follow the Gaussian orthogonal ensemble, which you have seen in this course of this conference. They have some very nice properties. So we just exploit only one of them, that if we take a matrix, random banded matrix, A and M, and suppose we diagonalize it, get all this eigenvalue spectrum, calculate their successive gaps, and calculate their distribution. If the width is very small, that is my band is very tightly banded around the diagonal, I'll say that there are only 3 diagonal elements. If I then this P of S shows something like a Poisson distribution, which is expected because the eigenvalues will be more or less independent of each other. But if I take a all-to-all coupling, they turns out to be the celebrated Wigner distribution. And this transition, I don't know whether this root n is not, I don't think it's an exact result, but typically this transition takes place at some critical width, which goes as say root n. Okay. So now we set up the problem. So we have these dynamical systems which are now going to evolve, calculate the corresponding Lyapunov exponent of the Lyapunov spectrum, and see where if I calculate the gaps of the Lyapunov successive exponents, what type of behavior they show. First, what we will do, we will take coupling to be very small. If we take the coupling to be very small, it's a typical snapshot. This is time. This is on this axis, the oscillators are arranged according to the value of their frequencies. Each of them has a different random frequency drawn from an uniform distribution. The plot looks quite irregular. But if I calculate the Lyapunov spectrum, it has got two distinct parts. One part, because of this chaotic, it's got a positive part, and it's got, since some oscillators have synchronized, it's got a negative part. Right, let me pick out these positive exponents only. They should be independent of each other, and and as expected, they should give us a Poisson kind of distribution. I should say Poisson-like distribution because we don't have any analytical proof for this. It just fits the Poisson function. And if I take the negative exponent part, which shows a strong repulsion as S tends to goes to 0, PS goes to 0. So it says that by the separating of the positive and the Lyapunov, positive and the negative Lyapunov exponent part, we are separating the two type of dynamics that is present. One dynamics is chaotic, that is due to the irregular behavior of the oscillators or the nonlinearity of the oscillators. The another part of the dynamics is the contribution is coming from the disorder present in the system. And since the disorder is governed by the underlying random matrix, then it reflects the statistics that was there that was present in the random matrix. So this can be better seen if we just switch off the irregular or the chaotic part completely. So I take the K, that is the coupling strength, to be very large, absurdly large, such that all the Lyapunov exponents are strong, all negative. Typically, one would say that this system is very boring because everything has gone to a synchronous state. Dynamics is not very interesting. But if I now calculate the distribution of the gap distribution for the banded matrix for which I change the bandwidth, I see that when the bandwidth is very tight, that is very narrow banded, I recover the Poisson distribution. That was the statistics one expects from the random matrix. and for the bandwidth is all-to-all coupling, it shows the Wigner distribution. Now to do a slightly better analysis, so one can fit a Brody kind of distribution, which is a one parameter distribution. As I tune alpha from 0 to 1, in 0 limit it gives me Poisson, in 1 limit it gives me Wigner, and I try to see as I vary this width, at what level the transition takes place. The system sizes are too small, but roughly it around the root n, below root n is Poisson-like, and above root n is Wigner-like. And if you see the corresponding spatiotemporal dynamics, it shows that there are many small clusters, like localized clusters, and they are synchronized, while for when the bandwidth is very small, and if the bandwidth is very large, there seems to be like some pattern in the system. So this can be understood. It's not very surprising if you see that what we are doing here, we are essentially writing an eigenvalue equation. When you linearize the system in the tangent space, is just finding the eigenvalues of this equation, and Lyapunov exponents are just log of those eigenvalues. If you are compare this thing with something, a system which is studied in quantum chaos context, like a Aubrey-Andre model, a tight binding model, then also we find the energy eigenvalues of this system, right? And it is very easy to identify that these two systems are not different if this thing holds good. And so where the Jacobian elements shows the disorder present in the potential, in this our case a space-dependent disorder, and the energy eigenvalue role is carried over to the Lyapunov exponents, and hence the Lyapunov exponents show a similar statistics. This can be further extended to a conservative system like a Hamiltonian mean field model. There also we see that depending on the depending on where we are, because this model shows a transition from a ordered state to the disordered state as I vary my energy per particle. The maximum Lyapunov exponent indeed captured that. Remember that in the either limits, u small and u large, the system is integrable. And when the u is very large, we retrieve the Poisson distribution. At the critical value of uc, in this case, it turns out to be 0.75, then I get the Wigner distribution. So that's some recent results. So this work was done by my student Mohanpur at IISER Kolkata. Thank you.
Any questions?
Yes.
So the Wigner curves that you showed,
yes,
have the peak at somewhere around 0.7 or 0.8. Is it because the mean spacings were not normalized to 1? Like for instance, this one is around 0.08 or something. No, it's at 1, but the value, for the standard Wigner, it's somewhere around 0.7 or 0.8.
This, I think this normalization, this value should be 1.
No, that is 1. Yeah.
Okay.
Yeah, it doesn't look, no, even the earlier curves that you had for Wigner, yeah, even this for instance.
Okay, I just shifted that the mean is equal to 1.
Peak has to...
Peak also has to go up to, yeah, that's not normalized.
Or 0.7 or something.
Yeah.
So does it follow from the properties of the spectral properties of the network that you are...
Yeah, so this was slightly, we just handpicked a particular kind of random matrix and try to see whether it produces that. I don't know if I take some random matrix of a different kind of statistics, whether that would be reflected here. So what is important is it shows something like there is some level clustering or level repulsion. So that much we can only say. But what remains invariant is that if I now change in the context of the Kuramoto oscillators, the distribution of the frequency, this doesn't change. So whether there is something universal, I don't know, but there may be.
So you called something coupling sensitivity to chaos.
Yes.
That was very confusing. I guess you meant that Lyapunov exponents are sensitive to coupling.
Yeah, I put it in quotes because I take it from somewhere.
Yeah, but you should only quote stuff which doesn't confuse other people.
No, they mean that the system is chaotic, but still there is some sensitivity to the coupling parameter as well, and the coupling of the Lyapunov exponents. Yeah, exactly. I mean, dependence of the Lyapunov exponent is sensitive.
Actually, what you're doing is you're taking a product of a lot of matrices, yes, and then finding the singular values, and then finding the the log of them. So, and then you're trying to do a spectral analysis in terms of nearest neighbor spacings. So there are known exact solutions to these problems when your underlying Jacobian matrix, let's say, is actually a Ginebra ensemble filled with, Gaussian independent IID variables. The entire spectrum is analytically known. So maybe it might be interesting to do such an analysis there.
What can be done for simple coupled map lattice type of system where the matrices are circulant, then
you can do analytically some of these things.
Anandamohan again, and I'll invite the next speaker.